I want you to picture a scenario that, well, it probably plays out every single morning. It's Monday. You've just poured your coffee, you sit down at your laptop, you crack your knuckles, and you open your email.
Oh.
You see a message from your boss about the Q3 reports. You see one from your mom asking if you're eating enough vegetables. And maybe you see one from a friend, let's call him Gary, about plans for the weekend.
Sounds like a pretty standard, peaceful morning.
It is. But think about what you don't see. Think about the chaos that isn't there. You usually don't see that message in all caps promising you 99 million email addresses for only $99. Or the one claiming to be a top-secret transaction involving a deposed prince who just needs your bank account number.
Right, because that digital sludge is, safely tucked away in the spam folder.
Exactly. And the thing is, we take that for granted. We just assume the computer knows. But when you actually stop and think about it, how?
Yeah, how does it know?
How does an inbox instinctively know that a message discussing the virtue of its nature and asking for a wire transfer is total junk, but an email from Gary saying, hey, pizza tonight, is important? It's not like there's a tiny person inside the server reading everything.
No, and thankfully not. That would be the worst job in the world. What is happening there is actually one of the most fundamental and successful applications of machine learning.
Okay.
Specifically, a technique called classification. And the star of the show today is a model that sounds like an insult, but is actually, well, it's a huge compliment. Naive Bayes.
Naive Bayes. It sounds like a philosopher who just didn't get out much. Or, I don't know, maybe a very gullible person named Bayes.
It does have that ring to it, doesn't it? But as we're going to find out in this deep dive, being naive in the world of computing is actually a superpower.
A superpower.
We are going to look under the hood of how computers make these optimal decisions and learn from data without actually understanding the context.
And we're basing this discussion on some fascinating lecture materials on machine learning and naive Bayes from Dr. Reza Abdali at California State University, Channel Islands. And the big theme here seems to be a transition.
Yes.
The source talks about shifting from traditional programming to acquiring models through experience.
That is the key shift. Instead of giving the computer a rule book, we give it experience. By the end of this, you'll understand why treating an email like a bag of jumbled words actually works, and why a billionaire flipping a thumbtack explains how computers avoid being overconfident.
I love the thumbtack story. We will definitely get to that. But let's start at the beginning. We threw around the word classification. In this context, what are we actually asking the machine to do?
So at its simplest level, classification is, it's a function. You have an input, which we call $6, and you want to predict a label or a class, which we call a new.
Okay. Input $6. Output yum.
It sounds like high school algebra, but I assume the inputs are a bit more complex than just a number. Just a bit. The variety of those inputs and outputs is wild. We just mentioned the classic one, spam detection.
Right.
The input is a document, the email text, and the classes are just spam, or ham.
Ham being the technical term for email I actually want, which I still think is funny.
It is the industry term, but think about OCR optical character recognition. There, the input is an image. A grid of pixels.
And the classes are the actual digits or characters?
Exactly. Or take medical diagnosis. The input is a list of symptoms, and the classes are different diseases.
That one feels slightly higher stakes than my spam folder.
Just a bit, yeah. It's also used in fraud detection, looking at account activity to flag fraud versus no fraud, and even automatic essay grading.
Which I'm sure students have mixed feelings about. But the common thread here, based on Dr. Abdali's notes, is that we aren't just coding if-then statements. We aren't saying, like, if the email contains the word money, then it is spam.
Exactly right. Because what if the email is from your bank? Or your friend asking to borrow money for lunch? A rigid rule just fails. So instead, in machine learning, we want the computer to learn the parameters, specifically the probabilities and the structure from the data itself. We want it to look at thousands of emails and figure out the patterns on its own.
So it's learning the vibe of spam.
Mathematically speaking, yeah.
Yeah.
You could say that. It's moving from hard logic to probabilistic statistics. And to understand how it does that, we have to talk about the model-based approach.
Okay, let's unpack this. The source uses a really visual example here to explain the model before we even get back to text. Digit recognition.
Right. Imagine a tiny image, say 15 pixels by 15 pixels. That's your grid. and drawn on that grid is a handwritten number, like a 3 or a 7.
Okay.
The computer sees this as a collection of features.
And features here just means the attributes used to make the decision.
Correct. In this case, every single pixel is a feature. Is pixel 3 on 4, on or off? That's a feature. You could have other features too, like number of loops or aspect ratio, but let's just stick to pixels for now.
Okay, so we have a grid of pixels, some are on, some are off. The computer needs to look at that pattern and say, that's a 3. Now, usually pixels in a drawing are related, right?
Yes.
Like if I'm drawing a line, the pixels touch each other.
Yes, and that is the crucial point. In a real handwritten 3, the pixels are dependent on each other. If pixel A is black and it's part of the top curve of the 3, then the pixel right next to it, pixel B, is also very likely to be black.
Right. You don't just have random speckles. You have lines and curves.
Exactly. Now, if you wanted to model that reality perfectly, calculating how every single pixel relates to every other pixel, the math gets impossibly heavy. It's what we call exponential complexity.
So too much for a computer.
Way too much. For just a small grid, you're talking about calculating probabilities for 2 to the n combinations. The computer would just churn forever.
So accuracy comes at the cost of impossibility. The universe would end before the computer figured out if I wrote a 3 or an 8.
Basically. So we cheat. We use the naive Bayes model, and the naive part is a bold, simplifying assumption. The model assumes all features are independent effects of the label.
Independent effects. Translate that for us.
It assumes that pixel A being on has absolutely nothing to do with pixel B being on, except for the fact that they are both caused by the number being a 3.
But that's a lie. Pixel A is on because it's next to pixel B in the curve.
It is a complete lie. It ignores the structural reality of the drawing. It treats the pixels as if they are all separate coin flips happening in isolation.
No geometry, just a pile of black dots.
Pretty much.
So if the assumption is demonstrably false, why do we use it? Why doesn't the model just fail miserably?
That is the aha moment of this entire deep dive. Even though the assumption is wrong about the structure of the data, it simplifies the math from an exponential nightmare to a simple linear calculation. And the kicker, it often works anyway.
It works anyway, even though it's ignoring the shape.
Surprisingly well. It turns out that to get the right classification, to just say this is a 3, you don't necessarily need to understand the perfect geometry of the 3. You just need enough aggregate evidence.
That is the computational superpower. Being wrong about the structure allows it to be right about the answer, but like millions of times faster.
Exactly. It captures the aggregate evidence effectively enough to make the right call. It's efficient, it's fast, and in many cases, it's just as accurate as more complicated models.
Okay, so that's pixels. But I
Yeah.
want to get back to my inbox. How does this naive concept apply when the input isn't a grid, but, a ranting email from a Nigerian prince?
So now we transition from image processing to natural language processing. And to do that, we use a model called bag of words.
Bag of words. I love this visual. It sounds so unscientific.
It is exactly what it sounds like. Imagine you take an email, you cut out every single word with scissors, you throw them into a bag, and you shake it up.
So the sentence structure is gone. The dog bit the man becomes the same as the man bit the dog.
Precisely. The model is insensitive to word reordering. It assumes the position of the word doesn't matter. It just cares if the word is there and how often.
Again, totally naive. Dear sir is treated the same as sir dear, or bank money is the same as money bank.
Right. But just like with the pixels, this simplifies everything.
So what does the computer learn?
It learns 2 sets of probabilities from its training data. First, the prior. That's just, generally speaking, how common is spam.
The source notes mention a split of like 33% spam versus 66% ham in the example data.
Right. So before looking at a single word, the computer already thinks there's a 33% chance this is junk. It's the baseline. Then it looks at the conditional probabilities.
This is the secret sauce.
This is it. Conditional meaning, given that it is spam, what are the odds?
Okay.
We ask 2 questions for every word in the dictionary. If the email is spam, what is the probability of seeing the word money? If it is ham, what is the probability of seeing the name Gary?
The data table in the source material is hilarious here. It actually lists the probabilities for specific words based on a training set.
Yeah, it's great.
Let's look at the spam indicators. Words like transaction, money, and this is my favorite, 2002 were high indicators for spam.
2002.
Was that just a big year for spam?
It must have been the era of that specific data set. But it shows how specific the model is to the data it learns from. If the training data is from 2002, the model learns that 2002 is a spammy word.
And then you have the ham indicators. Gary would, thought, and sleep.
Sleep. Apparently, spammers don't sleep, but Gary does.
He does. And there's a funny contrast in the source, too. The word subject is pretty neutral. It appears in both. But the word confidential, spelled with a C, mistakenly, that's a massive red flag.
Spammers and their typos, it's almost a signature.
It is. So the computer takes these probabilities, okay, transaction is likely, Gary is unlikely, and it does a calculation.
It multiplies them. It takes that initial 33% spam chance and multiplies it by the likelihood of every single word in the email appearing in a spam message. Then it does the same calculation for ham.
So if I get an email that says, Gary, I thought about the transaction, the computer's having a little tug of war.
Exactly. Gary pulls the score toward ham, transaction pulls the score toward spam, and the math decides the winner based on which pull is stronger statistically.
Simple. Elegant. But I feel like there's a trapdoor here. What happens when the system sees something it has never seen before?
Ah, yes. The zero probability crash. This is a massive issue with the naive Bayes approach if you aren't careful.
Let's set the scene. The computer have read thousands of emails. It knows money, it knows Gary. But suddenly, a new email comes in with the word morally.
Okay.
And let's say the word morally never appeared in a single piece of spam in the training data. Not once.
In that case, the conditional probability of seeing morally given spam is 0.
0.
And remember, we are multiplying probabilities together.
Oh no, I see where this is going.
Math 101. What happens when you multiply a string of huge numbers by 0?
The whole thing becomes 0. Instantly.
It destroys the calculation. It doesn't matter if the rest of the email is money transaction free Viagra. If that one innocent word morally has a probability of 0, the probability of the whole email being spam becomes 0.
So the model thinks it is physically impossible for this to be spam.
Impossible. The source actually shows a chart with odds ratios becoming infinite. If the probability of spam drops to 0, the odds of it being ham become infinite relative to spam.
It becomes infinitely confident in the wrong decision.
It's essentially saying, I have never seen this before, therefore it cannot exist, which is a real problem.
And the source calls this overfitting. Okay.
Exactly. The model fit the training data too closely. It memorized the past. It said, I have never seen a spam email with the word morally, therefore no spam email will ever contain the word morally. It lacks the ability to generalize.
Right. It lacks imagination. It's too rigid.
Yes. Dr. Abdali's notes have a great quote for this. Just because we never saw a 3 with pixel 1515 on during training doesn't mean we won't see it at test time.
So we need to teach the computer to be a little less rigid. We need to smooth things out.
Enter the concept of smoothing, and this brings us to the billionaire.
Yes, the parable of the billionaire tech entrepreneur. I love this example because it exposes how silly pure math can be without common sense.
So the story goes, a billionaire asks you, I have a thumbtack. If I flip it, what's the probability it falls nail up?
A weird question, but okay. You flip it once, it lands nail up.
Now, if you are a strictly maximum likelihood estimation robot, if you were just looking at the data you just collected, what is the probability of nail up?
Well, 1 out of 1 flips was nail up.
So 100%.
100%. The robot says, based on all available data, this thumbtack will land nail up every single time until the end of the universe.
And the billionaire says, why? Because that's ridiculous. Exactly. We know intuitively that one flip isn't enough proof. We have a prior belief that it could land the other way. We need to bake that intuition into the math.
So how do we do that? How do we stop the computer from being that 100% robot?
We use something called Laplace smoothing. Basically, we hallucinate a little bit of data.
We hallucinate data. That sounds like cheating.
It's constructive cheating. We pretend that we have seen every possible outcome just a little bit already. In the bag of words model, we add 1 to the count of every single word in the dictionary for both categories.
So even if the word morally never appeared in spam, we pretend it appeared once.
Yes. So now the probability isn't 0 out of 10,000, it's 1 out of 10,001.
Which is a tiny, tiny number.
But it is not 0.
And that saves the multiplication.
It saves everything. It keeps the probability alive. It basically acts as a prior belief that anything is possible, ensuring no single unseen word can crash the system.
It's like telling the computer, hey, keep an open mind. You haven't seen everything yet.
Precisely. It regularizes the estimate so the model generalizes better to the future.
So this brings us to the final piece of the puzzle. We're adding these imaginary counts. But how many do we add? Do we add 1? Do we add 10?
That is the question of hyperparameters. In Laplace smoothing, we call this value 10. If $10, there's no smoothing. If can-plen 1, it's standard Laplace smoothing. But we could pick other numbers.
And tuning this KL dollar, that's part of the learning process.
It is. But there is a golden rule here. A rule that if you break it, makes your results basically a lie.
That sounds dramatic. What is the rule?
You absolutely cannot look at the test set while you are tuning these parameters.
Why not? If I want the model to do well on the test, shouldn't I check how it's doing?
Because that's cheating. Think of it like a student studying for an exam. The training set is the textbook. The student reads it, studies the examples, learns the material.
Okay, that makes sense.
Then you have the test set. That's the final exam. If the student or the computer gets to peek at the final exam questions while they are deciding how much smoothing to use.
They aren't learning the subject. They're just memorizing the answers to the test.
Exactly. You're tailoring the model to that specific test rather than teaching it to learn the general concepts. So we introduce a third group of data, the held-out set or validation set.
So it's a three-step process.
Yes. 1. Learn the parameters on the training set. That's reading the textbook.
Got it.
2. Tune the hyperparameters, like tailors on the held-out set. This is like taking a practice quiz to see if you're ready. And 3. Only when you are completely done, you test the accuracy on the test set.
And once you run that test set, that's it. No takebacks.
That's your final score. That tells you how well your spam filter will actually work when real emails start rolling in.
It's amazing how structured this whole experimentation cycle is. It's basically the scientific method for algorithms.
It really is. It prevents us from fooling ourselves into thinking the model is smarter than it actually is.
So let's zoom out for a second. We've gone from pixels and words to probabilities and smoothing. When you look at naive Bayes as a whole, what's the big takeaway for you?
For me, it's the power of simplicity.
Yeah.
We called it naive because it ignores grammar, context, and sentence structure. It treats a heartfelt love letter and a Nigerian scam as just piles of words. And yet, it works.
It really does. It powers massive commercial technologies.
Right. Spam detection, digit recognition, language classification, all based on this dumb assumption that words or pixels are independent. It shows you don't always need to model the entire complex reality of the world to make a good decision.
A complex model isn't always a better model.
Not at all.
That is a comforting thought. Or maybe a terrifying one, depending on how you look at it.
Well, consider this final thought to leave you with. We kind of laughed at the bag of words model for assuming that word order doesn't matter. We think our communication is so nuanced and structural.
Right. Let's eat grandma is very different from let's eat grandma.
Yeah.
Punctuation and order matter.
They do to us. But if a simple mathematical model that completely ignores our syntax, our grammar, and our word order can accurately predict what we want to read and what we want to delete, what does that say about us?
Oh, that is interesting.
Are we actually that predictable? Is our communication less about how we construct sentences and more just about the specific keywords we choose to signal our intent?
Wow.
Maybe we are the ones who are naive about how complex we really are.
I'm going to be thinking about that next time I type an email. I'll be wondering, am I just signaling keywords to a robot right now? Is Gary just a probabilistic weight?
You probably are.
Well, on that slightly existential note, that wraps up our deep dive into naive Bayes. From spam folders to billionaire coin flips. Thanks for exploring the hidden math of our digital lives with us.
A pleasure as always.
We'll catch you on the next deep dive.